Hello everyone, thank you so much for joining us today. I hope everyone is doing well and staying safe out there. My name is Victoria and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences canceled due to COVID-19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all today to our webinar entitled Structural Integrity of Platform Wells. Before we get started, I would like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that's located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Elaine Whiteley. Elaine has over 8 years of engineering experience in structural dynamics and analysis of drilling risers, conductors, and offshore platforms. She has been based in the 2H Aberdeen office for the past 8 years, but recently moved to 2H in Houston. Elaine holds a master's degree in structural engineering from Heriot-Watt University in Edinburgh and is a chartered engineer with the Institution of Civil Engineers. And with that, I'll pass things over to Elaine to get us started.
Thank you, Victoria, for that warm introduction. I'm excited to be here today speaking on this topic, and I hope that you'll all find this information useful. So I'm going to start the presentation by talking a little bit about the system response of conductors and why it's important that we understand the response of our specific systems that we're looking at. I'll then go on to talk about some of the well integrity issues that we typically see coming up, and that will include corrosion, change in operational parameters. So that's not necessarily a physical well integrity issue that you would necessarily see, but it is something that has a significant effect on well integrity issues. And it'll also talk about loss of centralization. And you can see an example of that in the top right hand corner of that slide. That's from an inspection footage where the point of view is looking up through the guide funnel. So the white section that you can see, that's actually daylight. And you can see that there's a high level of marine growth on the conductor, and the bare pipe that you can see with no marine growth is where the centralizer was located. I'll then move on to talk about conductor ownership when it comes to integrity management, and I'll talk about the potential gap that there is in integrity management there. And then finally, I'll talk about the kind of processes that we can put in place to successfully manage the structural integrity. So why is it so important that we understand the system response of the conductor? It's because the platform conductor is pretty critical when it comes to the whole platform system. And most of the time it is the structural member that's supporting the well, so any potential issues with that then has consequential results inside the well, like downhole. I also talk about the system response. So the response of the system is the main factor in the structural integrity. So how the system responds to environmental loading dictates the magnitude of the bending loads, which then dictates the things like the connector capacity and whether that connector utilization is acceptable. And also the response of the system dictates what the stress profile looks like, and the stress is what drives the fatigue. So it dictates both the location that you expect the fatigue to occur and also the severity of the fatigue damage. Because the system response has such an effect on the well integrity, it's important to know that if you look at the integrity for the as designed system, if you are then looking at a system which in reality deviates from that design, then you're not necessarily looking at the system response of your actual as-built system. So it's important to consider if you have any deviations from the design, whether that's a change in loading or if it's a change in the ability of the conductor to resist the load. So that could be if you see corrosion significantly higher than you were expecting, that loss of wall thickness in your conductor then changes its ability to resist the load. So to understand the stress profile and what's controlling where the integrity problems are likely to occur in the system, we need to understand the factors that are controlling that stress profile. And essentially anything that's going to change the axial and the bending loads within the system are the factors that we're worried about or that we need to understand fully. So that's simple things like the properties of the pipe and the weight of the surface equipment above it, whether we have any application of tension. So that again, that's going to have a big effect on the axial loads within the conductor and the casing strings. And one that doesn't always see the attention it deserves is the thermal loading. So if you're looking at a system that is in drilling operations, a system that is in production or in injection. The thermal loads that you associate with production and injection mean that you're looking at very different axial states in your conductor during those operations. You also need to understand the structural support that the conductor has. So what lateral support does it receive? It guides and decks from the platform structure. And then finally, the environmental loading. Obviously, that's not one that we can control, but it is one that has a significant effect on the response of the system. So one of the first things to understand is the wellhead support system that you have in place for the conductor. So in the left-hand diagram, you can see that as a conductor-supported wellhead, and that is mimicking one where the conductor is latched onto the conductor. So that's a fairly typical setup that you would see. On the right-hand side of the screen is the opposite. This is a surface casing supported well. So rather than the conductor being the main structural component, it's simply acting as a shield to the environmental loading. And then one of the more complex systems is the system that you can see in the middle, which is a hybrid system. So this is where the wellhead is built that the conductor is supporting the well. However, the wellhead is not latched onto the conductor. So what this means is that during drilling, the conductor is supporting the well. However, if you move into production, the thermal loads can generate enough growth in the casings that they expand and essentially lift the wellhead off of the conductor. And what that means is that you're alternating between a conductor-supported well and a casing-supported well. So the reason it's so important is because it's the wellhead support system that mainly factors what the axial loads are that you see in the system. So both these diagrams represent the system just after drilling. So you've drilled the conductor, the casings. Your conductor is sitting in quite a high level of compression because it's supporting the casing strings that are being hung off inside the wellhead, and it's also supporting the surface equipment above. The casing strings, those are hanging under their own self-weight, so what they're seeing is actually a reasonable level of tension in those strings. And for a hybrid system and a lock system, at the end of drilling, they look pretty similar. As we move into production, we start to see the thermal effects from downhole, and what that means is that the surface casing is going to want to expand as it heats up. And in doing so, it wants to push up on the wellhead, but it can't move because of the wellhead and it can't move because of the hole, so it starts to go into compression. And it will do that until the point that it has sufficient compressive load that it can overcome the weight of the surface equipment and the internal casings. And what you'll find then is that that's when you start to see the wellhead move. The point is that once that's occurred, the conductor is no longer in the high level of compression that it was. It's now just sitting under its self-weight. But your casing string, which was under tension, is now in a reasonable level of compression because it's now the supporting mechanism for your well. Conversely, if you look at the locked system, the same thing happens. You heat up the internal strings, the surface casing wants to expand, so it sees this compressive load. But in addition to having to overcome the weight of the surface equipment and the well, it also has to overcome the axial resistance of the conductor because the conductor is locked to the wellhead. So what happens is that, again, the loads transfer until you reach an equilibrium in the wellhead, but because the conductor has been essentially pulling back on the wellhead to hold it in place, you'll notice that you see less movement in the wellhead. But it also means that because the conductor was attached to the wellhead, as the casing tries to push up, it's pulling on the conductor. And in the case where you have very high temperatures in the well, it's possible to put the conductor from a high level of compression into tension. And in the case where you've maybe got temperature but it's not as onerous, then you would still see the conductor have a lot less compression at the end of that than it did at the start. So these two systems looked almost identical during drilling, but you can see once you go into production that you're looking at two very different axial stress states in your conductor and your surface casing. So it's very important to understand what wellhead system you have and what that's doing to the axial loads in your system. As well as being concerned about the axial loads, we're also concerned about what a lateral support the conductor has. So whenever you have a slender structure like this, if it's in compression, you're immediately worried about buckling and you're concerned about what stability you have in the system. The easiest way to negate that is simply to apply tension. If you apply tension, then you're not concerned about the conductor buckling. But what you often find is that it's not possible to simply apply tension. It could simply be that you don't have enough deck space to get the tension system in there, and therefore you're not going to be applying tension. So we need to look at what we can do to limit the susceptibility to buckling. If you have a well like this, where you're looking at a tieback well, so you've got a subsea wellhead here, you're still going to have compression in your conductor, but the compression levels aren't going to be too onerous because the weight of the casings from the subsea wellhead down will be hung off at this location. So we're only really looking at the weight of the casing strings from the subsea wellhead to the surface wellhead. So we're still looking at a system though that's in compression, and the susceptibility to buckling is a factor of the compressive force that we're looking at, but also the span that the conductor is covering, so essentially from the mudline to the deck. So if we're worried about buckling, the easiest way to negate that is to reduce the span so that we're back to like a point where we're not worried about buckling occurring. This becomes more of an issue if you're looking at a conductor which is in heavy compression. So this could be because you've got heavier surface equipment on top, or it could be that you just have a very deep well, which means that your casing strings are incredibly heavy. Because we've increased the compressive load, to counter that, we need to have a much reduced span. So what you'll find is that for wells that are in high levels of compression, you would need additional lateral supports to be able to prevent buckling from occurring. So we know that we need to have lateral support to prevent the buckling from occurring, but the question is often, what centralization do I need? So it's not sufficient to say that you have lateral support, you also need to know what radial gap you have at that lateral support. So this is a typical well, it's got a few different guides. If we have a very tight level of centralization, so a very small radial gap, we're not worried about the system buckling anymore, but it will still take a deflected shape as the wave loading acts on it. And you can see here that because we have a tight centralization, as the conductor passes through the guides, it has to be located centrally within the guides because there's no room for lateral movement. If we increase the radial gaps that we see at those, then again we still have the deflected shape, but what you can see is that there's room for lateral movement. So in addition to the deflection, you also have lateral offset and movement of the conductor. And it's during this stage that you're going to see the higher motions, you're going to see higher curvatures, and ultimately higher stresses and a reduced fatigue life. So when it comes to fatigue life in particular, what we want to have is quite a tight radial gap to be able to maintain a lower fatigue damage rate. So another thing that we're often worried about for conductors is corrosion. And unfortunately for conductors, the areas where we're going to see the highest corrosion is also the same area where the conductor is going to see the highest loads. It's quite an onerous situation for the conductor. In the upper sections of the conductor, it's largely O2 driven corrosion. The conductor is just sitting in air. In the depths, down at sea level, below sea level, it's more microbial and anaerobic corrosion that's likely to be governing. But you can see that where you have the change in the water level from tidal aspects, that you have this oscillation where the conductor goes from seeing seawater to oxygen and seawater to oxygen, and it just creates this accelerated region of corrosion. So we know that that's going to happen, and we can plan that we're going to have some level of corrosion in the conductor, in particular probably high levels of corrosion in this area. But it's also worth noting that if you have a well integrity issue somewhere else in the system, can that then lead to a secondary problem somewhere else? And in the right hand side, you have a system, it's a casing supported system. So your conductor isn't a structural member, your casing is the structural member. And if your system is working as you would expect to have inert water in your A annulus and not necessarily concerned about particularly high levels of corrosion in your surface casing. However, if you have a subsea breach, like a mud circulation port, for instance, what you're then going to do is you're going to aerate and oxygenate the seawater that is in that A annulus, and then you potentially have this accelerated region occurring on your surface casing as well. And if your surface casing is your supporting mechanism, if you didn't design that would see that high level of corrosion, then you need to look at the potential structural integrity issue that you've now got a reduced ability to resist that load. So I'm going to go through a couple of project examples that show some results for looking at these different integrity issues and show the kind of effect that you can see. So I said earlier that the axial state of the conductor is quite critical to the performance of the system. What we have here is a large number of conductors that were grouped together based on their preload. So in this particular example, preload group 5 sees the least level of compression, and preload group 1 sees the highest level of compression. So at the point of design, you can see that actually there's not a significant difference. You're looking at a utilization difference of 0.3 and 0.4 across the range. Obviously, the one with the least compression has the lowest stress utilization. However, if we move towards higher levels of corrosion, in this particular case close to 50% corrosion, you can see that the system has changed. There's a larger spread between the groups, and also it changes your conclusion. So preload group 5, which has the least level of corrosion, is still acceptable, even close to 50% corrosion. However, preload group 1, which did the higher level of compression, is above the allowable that we would want. So although it didn't make too much of a difference at the design stage, that reduced level of compression means that actually when you do start to see integrity issues, you're in a better place to handle them. And it's also worth noting that although corrosion may be a significant issue, depending on the design margins that you have, even something like 50% wall loss is not necessarily the end of the world. However, that is going to be very dependent on the system that you have. So I also mentioned earlier that it matters what operation you're in, and particularly the thermal effect that's associated with those operations. So this is looking at a stress utilization plot for drilling, production, and injection as you go left to right. So because we don't expect to see much bending below the mudline, if you're looking in this region, this is the stress utilization essentially purely down to the axial aspect. So you can see that for drilling, you're looking at a utilization of around 0.18. As we move into production, that drops to just a little under 0.1, and that's because we've reduced the compression in the conductor, so that there's a lower axial utilization. As we move towards injection, it's the opposite, so we've actually increased the stress utilization, and that's because it's the opposite of production. So as you have the cold loads, the casing contracts and is essentially pulling down on the wellhead, further compressing the conductor. So it doesn't look like it makes too much difference. However, this is for a 100-year return period wave and current, and what you'll find is that the differences are more noticeable when we're looking at fatigue damage, and that's because without the high current damping it out, you see a larger range of stress motions between drilling and production. The other thing that we're worried about is stability when it comes to conductors, and the way we approach stability is we do a calculation and we base it on an interaction ratio, where an interaction ratio greater than 1 would indicate a susceptibility to buckling. So if we look, we can see we analysed it for drilling and we have an IR of 0.731. So that's perfectly acceptable, it's under 1. Note that that reduces quite significantly to 0.303 as we move into production. And again, that's because we have a lot less compressive loads, so our susceptibility to buckling is reduced. Injection, on the other hand, because we're increasing the compression, sees an increase in that IR value up to 0.972. So the point here is if we didn't consider the thermal effects that are associated with different operations, if during drilling we had a slightly higher result of something like 0.85, that would still be acceptable, but it would mean that when we then came to look at injection, you were potentially looking at susceptibility to buckling with an IR greater than 1. So it's important to consider the operations the conductor will see throughout its life, and particularly for strength and stability, make sure that you're considering the most onerous configuration that it will have. So if it's going to have injection operations, then we need to consider the cold loads that are associated with that. Now when it comes to fatigue, during the production, the fatigue life is much better than when it's in the injection state. So the fatigue damage rate in this particular example was around 3 times higher when it was in injection operations than when it was carrying out production operations. So when it comes to fatigue, we don't necessarily want to look at the most onerous. You'll find that if you consider only drilling C-state for the entire production life, that would be overestimating the damage significantly, and you might struggle to reach a target life of 20 or 30 years. What is appropriate is to consider the drilling for the drilling duration, and then to consider either production or injection for the durations that you'd expect those to occur. And for fatigue, we don't want to look at the most extreme event. It would be very tempting to consider production and look at the highest temperature. However, because it's the thermal effects, that would actually be under conservative. You should look at not necessarily the production that you see in the first few years, but the production rates and temperatures that you'd expect to occur for most of its life. So for fatigue, we want to look at the average kind of conditions. And then this is one that we see quite often occurring, is that an inspection goes out, does the inspection, and then we find that there's a centralizer missing somewhere in the system. This is an example where on the left we're looking at the system as it should be with centralization at all guides with quite a small radial clearance. And then on the right, we're looking at the loss of the centralizer at guides 4 and 5. So we now have very large radial clearances at both of those guides. And you can see the fatigue life has got significantly worse. And that's because guides 4 and 5, the centralizers there, those are the ones that see the highest load, and those are the ones that have the most impact on the effect of the results. So the concern here was that the system had been in this state potentially for up to a year and a half because they don't know the point at which the centralizers were lost. And actually, if this was the case where centralizers at guide 4 and 5 had been removed, then actually the fatigue damage was sufficiently high that all of its fatigue life had been utilized, which meant you wouldn't be able to go back onto this to complete the production operations because the fatigue life was already used up. So it's worth noting that this is the kind of effect that centralization can have. Obviously, this is the most extreme case where you assume you have no centralizers at guide 4 and 5. But what you would notice is if you have the loss of either of them, that you would see a shift left. And even if you had an increase in your radial gap, so from 0.5 inch to 1 inch to 2 inch, you would be shifting this profile left towards a much reduced fatigue life. So that's kind of addressing the well integrity issues that we're concerned about. And now we're moving on to talk about kind of how do we manage them and how are they managed at the moment. And there tends to be an issue that occurs for conductors regarding who has ownership of the conductor. So this comes up a few times. If you ask who's responsible for it, typically operators are broken down into multidisciplinary teams, and there's often a wells team and a structures team. And what I've found from experience is if you ask who's responsible, if you ask someone in the wells team, they think it's the structures team that's looking after it, and vice versa. If you ask the structures team, they think someone in the wells team is looking after it. And that is the problem, that the conductor falls down the gap because nobody is looking after the conductor if they think someone else is looking after it. So there's justification both ways. Yes, you could argue it should be the structures team. The conductor is often the structural member. It's supporting the well, it's supporting the surface equipment. It's also interaction with the platform structure. So yeah, it's very structural in that aspect. However, a well is just a series of concentric pipes, and the conductor is one of those concentric pipes. And as we've shown, the thermal loading down hole actually has a significant effect on the conductor on the axial state. So it's very much part of the well. So how do we manage this? And I don't expect you to read all of this slide, but it shows how complex the conductor is and why we see these issues regarding the ownership. So the conductor is affected by the platform interface. So it depends how many guides there are, what the radial gaps are at those guides. That affects the integrity and performance of the conductor. The surface equipment, what the weight of the surface equipment is, whether we have tension or arrangement, that all feeds again into the integrity of the conductor. We also have the well loads. So during drilling, what is the duration of the drilling, the mud density, that's going to affect the kind of ambient temperatures you see during drilling. And also, what is the temperature and pressures during production, because that's going to affect the axial state for the conductor for the majority of its life. So that's what's going to be impacting the integrity of the conductor. But it starts to get complex, because if you do a structural inspection and you see that there's corrosion, there's significant wall loss, that also needs to be fed into the conductor. But if you have a through wall loss in your conductor, that needs to be fed back to the wells team, because if you now have significant corrosion occurring in the surface casing, then the wells team need to then go back and look at the casing analysis and see what effect that has on the well itself. And it's because this loop starts to form here that makes the conductor so complex. And this is why it takes a holistic approach, and it needs multiple different disciplinary teams working together to make sure that you have all of the information that you need to fully understand the integrity issues that you're going to see in the conductor and to understand what your conductor is actually responding like. So what is the process for managing the structural integrity? Well, the first stage is to consider the conductor as a priority at the design, construction and operational stages. So a lot of the time we find that the platforms are already designed and have been finalized before the conductor is considered. So it's useful to have some flexibility in the platform design when the conductor is still being considered, because you may find that if you move a guide by half a meter or a meter, you could be making an order of magnitude difference to your fatigue life. So it's worth making sure that the design, not just of the conductor, but of the platform, it gives you the kind of optimum system that you could have. You need to be interfacing with the wells team at the design stage. That's to make sure that when you come to do the structural analysis, that you're looking at the correct load cases, that You're looking at the actual production kind of parameters you'd expect to occur for most of its life, and also that you're looking at the most onerous injection considerations when it comes to things like strength and stability. You then do the structural analysis. That's going to tell you how critical the issues are, things like fatigue life. It's also going to tell you which areas in the system you're concerned about. It might be a weld, it could be a connector, it could just be pipe body. And then based on that information, you would develop your IM plan. The next important stage is when you come to construction is to actually review the as-built system against the design. It's all very well on an IM plan, but if your IM plan if your system differs significantly between the as-built and the design, the IM plan that you created at the design stage may not be relevant to your system that you actually have in reality. So review the as-built against the design, and if there are significant changes, then you would need to go back, update the structural analysis to see if you're changing the severity or the location of the integrity issues, and then update the IM plan again. And then the most important thing is through operation to actually be implementing that IM plan. It's also useful to utilize inspection and monitoring data. A lot of the time the inspections are carried out, but not a lot is done with the data. If you can take wall thickness measurements or corrosion images, if you can see that it's increasing at a rate quicker than you would have expected, then it's useful to know that in advance rather than finding out 10 years down the line once the corrosion is too significant that you're then going to look at a much more significant problem further down the line. Effective management, so that comes back to the holistic approach, multidisciplinary teams working together and sharing that information. Potentially ad hoc structural analysis, so again, if you do an inspection and you see that there's a centralizer missing, you might need to do structural analysis to figure out what effect that actually has on your system. If the centralizer is lower down in the system, it might not be a big problem at all because a lot of the time the lateral motions have dissipated towards depth. So a centralizer that's missing at the bottom might not require analysis and certainly would be unlikely to require remediation work. However, if it's a centralizer that is at the guide either side of the sea level, then yes, that one's likely to result in remediation work being required. So this is just a sort of short introduction to managing structural integrity, but 2H, along with our sister acting companies, Claris, Pulse, Claxton and Core, have been working on a guidance note with the Energy Institute titled Guidelines for Integrity Management of Offshore Platform Conductors. So that's actually due for publication in the next few months, so between Q2 and Q3 2020 it should be published. So if you keep an eye on the 2H social media sites, you should find that there will be a post in the next few months detailing when this is being published. So just to conclude, the best way to manage the integrity of the conductor is to have a really good understanding of the system, know where the critical areas are, and also know which parameters are going to have the most effect in changing that response. Things like corrosion are going to occur and there's not really a lot you can do about them. You can make sure that your system is designed to accommodate for them, and then all you can do after that is to monitor it and compare it with the design allowables that the system has been designed to withstand. The way I would define a conductor is that it's a safety critical structural member which forms part of the well, and it's because of the complex role of the conductor that it makes managing the integrity a little bit harder maybe than some other components, because it requires multiple different teams working together and trading information, sharing information to fully manage the integrity management of the conductor. And that integrity management should be done throughout the life of the system. So it needs to be a focus at design stage, and then needs to be a focus during construction, and then throughout the operational life. So thank you very much for listening to me today, and if you have any questions, I'll be happy to answer them.
Okay, great. Thank you so much, Elaine. We do already have a few questions, so I'll get started asking those. First question, what would typically cause a loss of centralization?
So loss of centralization is typically caused by the bolts backing off on the centralizers to the point that it doesn't have the compression to hold on to the conductor. What you'll sometimes find is that when the centralizer releases, it just slides down the conductor, or the bolts open up enough so that it essentially just unclamps itself from the conductor. Thankfully, it's something that you typically see in older wells, like from the 80s and the 90s, where centralization itself wasn't really given much of a consideration. What you'll find now is that centralizers are designed to withstand the maximum lateral load from the analysis that you would expect to occur, and they're also designed to have sufficient fatigue life. So For newer wells, it's not something that we'd be as concerned of, but there are a lot of older wells out there at the moment, and certainly we're seeing that several of them are having issues with the loss of centralization.
Okay, perfect. Next question. How are the operators dealing with all this inspection, rework, or redesign, if needed, to keep the integrity, especially in the current oil and gas downturn?
So actually, managing the conductor and staying on top of the integrity management, it's usually cost saving in the long run. So if the analysis has already been completed, if you're looking at changing the centralization, it's not like you're starting all the analysis from scratch. You're simply making a tweak to the model and rerunning existing analysis. So it's actually quite quick and it's quite cheap to do, to look at a revisit to a centralizer. Or even if you're changing things like the wall thickness or because of corrosion, it's quite cheap to make small changes to existing models and then to understand what your response of your system is. Because the answer may be, like you saw, that you have a high level of corrosion, but actually, if your system has margin, then it's not actually a problem, so you don't need to be concerned about remediation work, which can save large sums of money. So, as long as you're staying on top of it and you're kind of predicting it, if you can assess whether it's required, and if it's not required, then you can rule out, you have analysis that says we have an issue but it's not a problem, you immediately then don't have to be concerned about remediation. And if you're still carrying out inspections, if you can foresee in advance that you have a problem that is occurring but it's not going to be a significant problem for a little while, then it gives you that time to plan, try and fit the operation, the remediation work into existing planned schedules, rather than kind of ignoring the integrity of the system, and then all of a sudden you're looking at a very expensive problem because you're looking at something that has to be done there and now. So yeah, as long as you're kind of looking after the integrity management, in general, it should be cheaper in the long run.
Okay, thank you. Another question on slide 14 specifically, can we increase the number of centralizers to have better fatigue life?
Yeah, so typically if you've got a larger number of guides, and especially if you have a tight centralization, then you've got less room for lateral movement, so you would typically find that your fatigue damage would be reduced.
Okay. Let's see. A conductor is usually very robust. Would you really expect to see it buckle?
So it's really hard to picture something, especially like a larger conductor, like a 36-inch by 2-inch conductor buckling. But they have high loads that they have to accommodate. So like a lot of the casing strings, especially the longer casing strings, the compression loads in the conductor are significant. So it is possible that you would expect it to buckle. However, to actually see it buckling would not be as likely. What you'll find is that it will want to buckle, and as it does that, more often than not, something will snag. So the centralization in the guides will get caught, or the wellhead will get hung up on decks. So you're very unlikely to see the conductor buckle to the extent that it drops to the seabed. But you would see instability in the conductor that would be attempting to buckle, but physically you probably wouldn't see it fully buckle.
Okay. Next question. How does marine growth affect the structural integrity of the conductor?
So the marine growth, it affects it in a number of ways. So the first one, we said that we're very concerned about the axial state that the conductor's in. So if you're in production and you've got marine growth, the hard marine growth, the density is something close to concrete. So you're looking at quite a significant weight that can be added to your conductor, and that's just adding to the compressive loads that we have. And also marine growth is adding to the diameter, the OD of the conductor, and the drag diameter. So you're actually increasing the loads on the conductor. So in general, marine growth is quite onerous to the conductor. It makes the compression worse and the loading worse. So that's usually accounted for in the analysis. We would assume, depending on the area, what kind of thickness of marine growth we're looking at and what type of marine growth is occurring, and that would be accounted for in the analysis. Although there are potential benefits to it, because from some of the footage that I've seen, I think there are probably several centralizers in the North Sea in particular that are being held on by marine growth. So it's not all bad.
Cool. Next question. What are the options available if analysis shows there is an integrity problem which isn't acceptable?
So again, it comes back to the analysis side of things. It might seem like a problem, but it's worth doing analysis to make sure that it is actually as bad as you think it is, because you might be able to negate remediation work by doing analysis. If it shows that, yes, the problem is significant and that in its current state the system is not acceptable, then remediation work would be required, but that would be very dependent on what the integrity issue was that you saw. So on the very first slide, you saw the picture with the centralizer missing. Below that, there was a couple of pictures of a conductor with a sort of lightning bolt shaped damage to it. And underneath that, there was a stress plot from local FEA analysis. So that was actually a system that we analysed, and because of the damage to it, that section of the conductor, the strength and performance of it was much reduced. And because of the shape of the damage, there were stress razors which were causing incredibly high stresses in that section of conductor. So the remediation work in that example was that we, 2H, designed a clamp system to go around the conductor. So what you do by doing that is you're transferring the load not through that section of conductor, but you're transferring it through the clamp that you've installed. So the conductor below that point was perfectly acceptable. So all we had to do was to strengthen that upper section to bring it in line with the rest of the conductor. That's quite a popular way to address like a localized weakness in the conductor. And another option for that is, rather than considering the conductor and the casing separately, you can grout the A annulus, so you end up with a composite pipe where your surface casing and your conductor are working together. Although I would add that you need to be quite cautious with that, because if you do that, as you remove the load from the 30-inch, it's because you're adding it into your surface casing. So you would need to know that you have enough margin in your surface casing to be able to accommodate that increase in load.
Okay, perfect. That is all the questions that we have for now and the time. So thank you so much, Elaine, for all the information on the topic. As I mentioned earlier, if you'd like to continue the discussion, please contact Elaine directly using the details provided here. And thank you all to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening every 2 weeks during our time at home. Check out the 2H website for more details and to sign up. And again, please look out for the recording of the webinar in your email in the next 24 hours, and we hope that you all enjoy the rest of your day. Thank you.
Thank you.